Okay, I think we can start again. So we will continue with a couple of examples of plant monitoring, and then we will switch to pollinators and plant-pollinator interactions. And the first presentation of this afternoon is by Don Water from the University of Wisconsin at Madison. And he's going to present some results obtained with the forestREplot program. Thank you, Don.
Thank you, Emmanuel, for getting such an interesting group of people together. I'm too many conversations I don't want to miss. We have, of course, the same situation and problems in North America as you do in Europe in terms of rapidly changing environments and various components of global change. I want to talk about my research today. I'm part of the forestREplot network based here in Ghent, Belgium, but the questions and problems and even approaches are going to strike many of you as very similar. I'll begin by discussing some of the forces driving ecological change. And the world, of course, is changing in more ways than one. But my emphasis here is how crucial it is to have data and how rarely we have good baseline data from many decades ago, making those data very valuable and making it important for us to think carefully about how we design our monitoring systems as we look into the future. I will focus, as I said, on the forests of North America, and in particular my home state of Wisconsin and the upper Midwest above Chicago. I will focus also on changes in abundance, and I'll define that in a moment. And these are some of the points I will make. I want to talk not only about understory forest herbs, but also about the regeneration of forest trees, which is changing radically in eastern North America right now. And ultimately, I want to return to this question of are plants responding to declining pollinators, or are pollinators responding to declining plants, or perhaps both? If we begin with what Emmanuel defined as opportunistic occurrence data, it struck me early on in my own research that we had only a handful of studies from around the world looking carefully at species enumerations from as long as a century ago, but that every one of these studies I could put my hands on anyway, at this time in 2004, it seemed as though locations, even protected locations that were in parks or specifically natural areas, were losing a massive proportion of their total species at a rate that varied between a third of a percent and 2% per year. And the fact that all these studies were showing such dramatic declines, to me, suggested we need more systematic monitoring. One of the ways in which the world is changing, of course, is climate change. We get lots of attention to this now. In Wisconsin, we know over the past 50 years, temperatures have become hotter. We've also got more intense precipitation occurring, including the tornadoes that were in my state the last few days. And if we look into the future, we can see that those trends will continue, essentially moving Wisconsin down to Iowa or maybe even Arkansas in terms of climate. Our own research looked at how plants are responding, or have responded already, over the past 50 years to these changes in climate. And we found that most plants were moving northward and westward, as you might expect, as the climate was changing. But we also discovered that most species were moving at a rate much lower than what would be necessary to keep up with climate change, echoing the remarks that you heard this morning about what was going on in plant groups relative to other taxonomic groups. Another way the world is changing, of course, is habitat fragmentation. As humans grow denser on the landscape, we tend to build a lot of roads and houses. So the same site that we studied in southern Wisconsin in 1950 that was surrounded by agricultural lands, a good forest, is still a forest in 2000s, but it's now surrounded by suburban development. So the landscape context has shifted. Another way the world is changing, of course, is atmospheric pollution, including nitrogen and sulfur deposition. A national study I was affiliated with looked across the United States and discovered that many forest understory herbs are being negatively affected by nitrogen. Of course, I'm not showing you the graph of the ones that were not affected very much by nitrogen or even benefited from the nitrogen addition. But in our own set of sites in Wisconsin, in a general linear model, we discovered that nitrogen, and I was the skeptic here, I did not expect nitrogen to be having much of an effect in such a restricted geographic area. And given that we're not in the industrial valley that gets most of the nitrogen pollution in the US, I was shocked to see that we were losing species diversity in response to nitrogen deposition as well. Going back 50 years, the reason I can present you the results I'm showing you today is because John Curtis and his students decided to systematically study the vegetation of Wisconsin, the plant communities across the state. They visited actually more than 1,000 sites, and it was an incredible effort. 20 students did most of the actual field research. And the sampling layout that they used in the 1950s involved an array of 1 meter square quadrats. And they used, unfortunately, only 20 of these. I consider that now a serious undersample. So when we revisited these sites in the 2000s, we used between 42 and 120 1 meter square quadrats at each site in order to sample more completely the vegetation that was there. This, of course, involves statistical corrections for making fair comparisons between the periods. That stripe you see across Wisconsin represents a shift in climate and corresponding vegetation community types. Northern Wisconsin continues to be covered primarily by forest. It's a forested matrix, whereas southern Wisconsin is primarily agricultural now and was originally more prairie and savanna. As I said, I'll focus on abundance, by which I mean the proportion of the 42 to 120 quadrats or sites that were occupied, the frequency at which species occur. Someone compared it earlier today to a pin survey where you have a very big crude pin that's going down. There are two components, of course, to plant abundance. The first is the number of sites that a plant occupies, a given species, and the second is how abundant that particular species is at that site. And it's not surprising that there's a correlation between these two. Species that are widespread at many sites also tend to be more abundant within those sites. And of course, what was true in the 1950s is still essentially true in the 2000s, in that there's a lot of demographic inertia. Species that were originally most abundant in the 1950s mostly remained abundant in the 2000s. In fact, Myanthemum canadense, the most abundant species we found in northern forests, became even more abundant by the 2000s. What's interesting in terms of this path model is that we found an effect of the number of sites occupied in the 1950s on the local abundance 50 years later. This is, I think, a manifestation of what we call the rescue effect, where the more prevalent a species is in the landscape, the more likely it is to colonize or recolonize a given site. This demographic inertia is still obvious if we look at the individual abundances of species across the 50-year time span. You don't have zero, so when you switch to logarithms of abundance, you have a smaller sample size, but the correlations here are very high. But you'll also notice the considerable amount of variation. Many species were changing substantially in abundance despite this inertia. If we focus first on the more fragmented, smaller forests of southern Wisconsin, you'll see that, and this was a community type of 4 or 5 that we analyzed that suffered the largest losses in diversity over the last 50 years. All of these, by the way, were originally chosen to be natural areas representative of their community type by Curtis. And all of them remain substantially intact. We never sampled sites that have been impacted by any major form of disturbance. So these should be reasonable replicates of what some people would call ancient forests here in Europe. Nevertheless, they lost 25% of their original plant richness on the 1 square meter basis, and at least a fifth of their diversity over 20 square meters, and that 80% of the sites managed to lose species over the 50-year interval. As also pointed out this morning, the changes in beta diversity, which we should be paying attention to, are at least as dramatic. This McDonaldization of the world means that the sites become more similar to each other, and also even within sites, individual quadrats, the 1 meter square quadrats, begin to look more and more alike as you sample them. This fact that these forests in southern Wisconsin were fragmented means there was a distinct pattern. These losses are not random. They're not random with respect to sites, and they're not random with respect to species. Let me talk first about the sites. It was the sites that were smaller, that is, that were more, represented less forest area and tended to be more isolated from one another, that lost more species. This is a clear manifestation of what many have called the extinction debt, derived from island biogeography. The relationship between species richness and area that was almost as small as 8% R squared in the 1950s has become far more dramatic by the 2000s. What we don't know is, if we look at the next 20 or 50 years, whether that line will continue to steepen, whether the extinction debt has already been paid, or whether we still owe species. If we turn now to individual species, the effects there were non-random as well. The main metric I decided to analyze for this talk is the log of the proportional change in abundance. By what proportion did a given species increase or decrease? Of the 274 species I analyzed for that, just over a third increased over the last 50 years, but almost 2/3 decreased. And that mean change in abundance is highly significant and negative. So it represents a 39% decrease in abundance for the mean species. And native species declined a bit more than that, whereas non-native species increased almost 6 times. So you can see there's a clear difference in which species increase. There's an eccentric method developed by a man in Chicago called the coefficient of conservatism. I don't want to go into the details, but suffice it to say that the ones that are ranked 0 and 1 are relatively common, and 0 in particular are introduced exotic species and very cosmopolitan, widespread species. And 6 through 10 tend to be habitat specialists, restricted in their range or their habitat preferences or both. And not surprisingly, you'll see that the introduced non-native species and the already common species are the ones that have increased over the last 50 years, where almost all the native species that don't fit that category declined. Some of these names may be familiar to you in that we imported many of our species from this part of the world, like myself. But in addition to the human invaders, there were a lot of biotic invasive species. And so I feel on familiar ground when I visit Europe, having met many of these back in America. Here are a couple of what my student Dave Rogers calls native invaders. The Parthenocissus, or Virginia creeper, and the geranium maculatum, already quite common in the 50s, became even more common. Vines in particular may be increasing because of increasing CO2. Lianas in general are getting more abundant in tropical as well as temperate forests. But these invasives like Rhamnus and Alliaria have really taken off as well. These are species that are probably familiar to you already, but we saw 45 of 94 sites in southern Wisconsin, now including this garlic mustard area, and likewise the same number of proportion of sites now hosting Rhamnus cathartica. Linicera comes from Asia, but it too has invaded many, many sites. What's interesting to me about all three of these species is that they modify the soil, they modify conditions. They benefit from high nitrogen soils, for example, and they also tend to entertain invasions of Eurasian earthworms. And together with the earthworms and high nitrogen leaves, they tend to change soil chemistry and nutrient cycling in ways that may favor what some people call an invasion cascade. The winter species in northern Wisconsin were a somewhat different mix. They included many ferns, a toxic plant, Erythema triphyllum, that's protected by rafide crystals of calcium oxalate, and again, several invasive exotic species. But this increase in grasses and sedges was dramatic and surprising to some of us. Native rare sedges, by the way, didn't increase. Some of them even decreased. But the commonest sedges did very well. This would be a matter for perhaps idle speculation or discussion were it not for the fact that these invasions have impacts. Some people have argued that invading non-native species are just passengers rather than drivers of ecological change, that they just kind of add to the size of the party going on in any given biological community. But these data, or these results anyway, suggest that's not the case. That winners moving in means that loser species are displaced. We tested Hubble's zero-sum assumption there and looking at how much the change in losers at a site was associated with a change in winners. You can see clear evidence for a trade-off there. And looking at 70 native species in southern Wisconsin forests, we found negative associations overwhelmingly. So those are the winners. What about the losers? Well, of interest to this group is the fact that the losers were the pretty wildflowers with insect-pollinated flowers. So in southern forests, they included these species. I'm sorry, I apologize for the common names there, but you probably know them by their proper names. And here's some Latin binomials for the losers in the north. As I just noted, these are species that your citizen naturalists and botanists both kind of delight in seeing and identifying. But their change in abundance is something we might be concerned about, because if animal-pollinated wildflowers are declining, that might represent a limited resource for pollinators and helping to account potentially for some of their decline. We looked at whether there was any association between the mode of seed dispersal and whether a plant species has increased or decreased over the last 50 years. And we could not find any such association, except for the fact that some of the non-native species, those that had internal animal dispersal, had a higher rate of increase. So they're getting around well. External animals also associated with some of those invasives. More interesting is the interactive effect we found between the pattern of increase or decrease in a species and its dependence on specialized animal pollinators. That middle category there, it's mostly wind pollination on the left and mostly those disc-type unspecialized flowers we heard about on the right. But if we look at the middle class of specialized flowers, the non-native invaders benefited. They increased even more if they had that mode of pollination, where it was the opposite for the native species. So they'd actually decline more if they were dependent on specialized pollinators. This is also reflected in this graph, where we see that the loser species in the northern Wisconsin sites were overwhelmingly biotic pollinated, whereas the winners were split almost 50-50 between wind pollination and insect pollination. So we're losing insect-pollinated species, we're gaining wind-pollinated species in the northern forest, so that a lot of that reflects the grasses and the sedges, and therefore it could be a side effect of something else driving those changes. And that something else is what I want to talk about next. Let's turn our attention from the understory herbs in our forest to trees. We do have a very structured monitoring system, again to use Emmanuel's phrase, in terms of the U.S. Forest Service Forest Inventory and Analysis System that's been going on to mostly measure wood or tree volume in the forest since the 1940s or 30s even. They've recently expanded that program to try and pay attention to the understory, but it's a very late add-on, and we don't have very long or many of those data. But within Wisconsin, we had 13,000 plots to look at, sampled between 1983 and 2013. And we decided to look at the number of 1 to 2 inch or 2.5 to 5 centimeter saplings. Many species, like the red maple you see there, have a log normal distribution of the number of those smaller saplings. That's, okay, I'm almost there. But we discovered that Thuya, Tsuga, and Pinus strobus had this extraordinary, highly skewed distribution with essentially mostly zeros. There were no saplings we could find of those species, even when they were present in the overstory. And we began to suspect that white-tailed deer might be responsible for some of those patterns. We constructed a path model here that looked at how deer density varied over a 35-year period, and likewise the number of saplings. And we discovered that there were strong effects of deer density in the preceding period on the number of saplings present. And in fact, these direct effects tended to add up with the indirect effects to create rather astonishingly high beta values by 2011. Showing that these effects of deer browsing accumulate and have suppressed the number of these saplings in Acer and Populus. Deer populations have increased not just in Wisconsin, but across the eastern, southeastern, Texas, western states, British Columbia, and here in Europe as well. You've had increases in deer. And so, and these increases are associated with dramatic decreases in the ability of species like this Quercus rubra to regenerate. So I'm suggesting to you that deer are having an effect not only on trees, but also on the understory herbs as well. In many cases, those pretty wildflowers or the bright fruit that we associated with Clintonia act as flags to attract a deer's attention, and they tend to preferentially browse those species. This has become such a problem that a new term has popped into view, the regeneration debt. We can add to our extinction debt now. And to summarize, many forces threaten plant diversity: climate change, deer herbivory, and fragmentation, nitrogen deposition, invasive species. These have contributed to 50-year declines in community diversity at most sites, beta diversity, and the abundance of a majority of the understory plant species in Wisconsin forests, especially those with specialized flowers and pollinators. I think it's probably some combination of those factors, deer herbivory and all those declines in the specialized, more specialized dependent plant species that are creating the situation we have now. But the point I want to leave you with is that none of these results would be known were it not for those data taken decades ago, so that without these changes are completely invisible unless and until we can get some kind of long-term monitoring in place. So I assume we're going to have some interesting time tomorrow discussing what metrics and methods to focus on. But another question I've been left with is whether declines in pollinators reflect a decline in floral resources, or whether declines in floral flowers may also reflect declines in pollinators. Thank you.